Although Cloud SQL provides a lot of great features out of the box, it doesn't provide load balancing between replicas. Without this feature, we can't distribute the work and we can't implement horizontal scaling using the read replicas. So, in this tutorial, we'll implement a load balancing solution using Google Cloud SQL for Postgres and HAProxy. For this recipe, we'll need a Cloud SQL database for Postgres with one or more read replicas, a Cloud Compute Engine instance to run the HAProxy balancer, a configuration file to describe the load distribution behavior. Additionally, some shell scripts can be added to facilitate automatic updates when read replicas are added or removed from the Cloud SQL instance. And, for simplicity, we'll run the client applications on the same machine as the HAProxy. Scaling reads and scaling writes are complex subjects, each with its own set of benefits and issues. Therefore, it's best to treat them separately and one at a time. In this tutorial, we'll implement load balancing only for the read connections. This means that read requests are always available, which will take us one step closer to high availability. Given that read-only requests will connect to the HAProxy, and from there they are distributed across the replicas. On the other hand, the write queries will connect directly to the primary instance of Cloud SQL. We can scale only the read requests and still benefit a lot. Normally, applications are far more likely to read some information multiple times from the database before making some changes. Now that we have some basic understanding of the architecture and the key components, it's time to play with Cloud SQL. The goal in this tutorial is to build a highly available system for the read requests. To start, we'll create a brand new PostgreSQL primary instance and two read replicas. In the Google Cloud Console, on the project selector page, we'll create a new Google Cloud project. We do this so that after we finish this practice session, we can easily delete the project and all the associated resources will be deleted as well. We give it a name, load balancing Postgres, load minus balancing minus Postgres. Then, in the Google Cloud Console, we go to the SQL Instances page. Here, we create an instance. We choose the database engine, Postgres. We'll have to enable the Compute Engine API. Then, we configure the primary instance. We give it a name, primary. A default user called Postgres is already created, but we'll have to provide a password for it. So, we add a dummy password here, which we'll have to remember. We select the latest version, PostgreSQL 14. The region is not important for this tutorial, but to simplify the configuration, we recommend that you launch the Cloud SQL instances and the Cloud Engine instance to be in the same region. This will simplify the network setup because it will allow instances to communicate with each other using only private IP addresses. Otherwise, for more complex network layouts, we'll need to consider firewall rules to allow connections and also to enable SSL certificates. We'll use a single zone since we don't need high availability for now. For the machine type, the smallest one is okay, so we choose lightweight. Also for the storage, 10 GB is more than enough. Furthermore, we should also set up the private IPs. And finally, we create the instance. This will take a couple of minutes. Afterward, we create two read replicas. So, create replica, we give it a name, replica-1, and create instance. This will also take some minutes to be built. As a side note, the main use case of a read replica is to increase the read capacity. In Cloud SQL, read replicas don't provide failover capability. In order to be able to use the replica for failover, it has to be a cross-region replica, which is a different kind of component. Then we create the second read replica. Last, we should also create a test client user. We could simply use the default one named Postgres, which also has all the permissions. However, the best practice is to follow the least privilege rule and use a separate unprivileged user account for each purpose. So, we add here a new user and we name it test_client. The next thing to do is to create a Google Cloud engine where we'll run the HAProxy tool. So, create instance, we'll name it HAProxy, we leave the same region as for Cloud SQL, an E2 micro machine will be sufficient for this demonstration. Then, for the operating system image, we'll go with the default. This is Debian with version 10 of Linux. Keep in mind that depending on the operating system, software installation steps might differ a little bit, and also the configuration file locations may vary, but the principles are the same. Next, we'll connect to the instance via SSH in order to install HAProxy. First, we update the package index so that we have the latest packages. Sudo apt-get update. Then we install the load balancer. Sudo apt-get install HAProxy. Next, we should check if we can connect from this machine to the PostgreSQL machines. To do that, we'll use the Google Cloud SDK, which comes pre-installed. We can confirm this by running the command google cloud ---- version. Then, to make sure that the SDK is authorized to connect to the PostgreSQL instances, we can call Google Cloud SQL instances list. This would list all our SQL connections. But since that we are not authorized yet to access the SQL instances from here, to enable the access, we should enter the details page of this instance. Then, we look for the API and identity management. And here we see that the Cloud SQL access is disabled and also the service management is read-only. So we should change this. Edit. Still, we are not able to modify these settings while the instance is running. We should stop the instance first. Now we select Set Access for each API and enable Cloud SQL, and for the service management we set it to read-write. We save the changes and then we start the instance. Now, we should be able to list our Cloud SQL instances like so. We should also enable the Cloud SQL admin API. Yes. Now that the connections are open, we are ready to set up HAProxy. There are 4 essential sections to an HAProxy configuration file. These sections define how the server performs, what your default settings are, and how the client requests are received and routed to your backend servers. Normally, on Linux systems, the configuration file is placed under /etc/HAProxy. Here we'll find a sample file, but we won't use this one because it has too many parameters which are not related to the load balancing subject. However, you can keep a backup of it if you want using the copy command. Now, first, we'll clear the content of the current file. To truncate the content, we can call greater sign and then the name of the file. But we should also have write access for this. So, sudo change mode give read and write access to all the user for the HAProxy file. Then, to write in the file, we'll use the nano tool, sudo nano haproxy.cfg. First, we have the global section where we'll specify a single parameter called max connections. We set the global connection limit to 100 connections. Basically, this is the number of connections HAProxy will manage. After this number, extra requests will queue in the kernel buffer. Then, we have the defaults section. Here, we want to set the load balancing mode. HAProxy uses HTTP by default, and we must change this and set it to TCP instead. We may leave it to HTTP only if HAProxy is expected to inspect the HTTP messages of the incoming traffic. If not, it's better when the mode is set to TCP because it operates faster. After the essentials are set, we can also define a number of connection retry and timeout values. Of special note are the server and the client timeouts. This will break the connection if either the client or the server is idle for more than 5 minutes. We also set the connect timeout to 5 seconds so that HAProxy doesn't wait forever to establish a connection. These parameters are all subject to usage patterns, so feel free to modify them to better fit your cluster needs. And finally, we set the timeout for the check function to 5 seconds so that once a connection is established, it isn't alive for much longer than necessary before being disconnected. Once we've taken care of the connection's behavior, we must define the frontend and the backend actions. We create a new frontend named ft_postgres, and here HAProxy will handle incoming connections. So, within the definition, we set the bind to all IPs and the port 5432 so that it looks just like another PSQL server. This bind setting assigns a listener to a given IP address and port. In our case, the IP can be omitted to bind to all the IP addresses on the server. And the port can be a single port, a range, or a comma delimited list. Then, we link this frontend to a backend. We'll name the backend bk_postgres. So next, we create the backend we mentioned earlier. For the routing algorithm, we'll use the least connection one instead of the default round robin. The default one can lead to workload imbalance due to the fact that some replicas receive more sticky connections than others, and this approach helps to spread the query load more evenly among the replicas. Also, if multiple nodes have the same amount of connection, then the algorithm will simply use the round-robin method. The purpose of the backend is to forward connections to the read replica servers. Therefore, here we should specify the read replicas. Each server line will come in three distinct sections. First is the server ID name, second is the host and the port for this service, and third are further options for this definition. To get the server names and IPs, we can check the Cloud SQL page. Here we chose some basic server names, such as replica-1, to make it obvious what is expected. So first, we specify the server ID, then we copy-paste the server IP, then the port is 5432, and the option is check. Then we do the same for the second server. We save the file and close it. After we are done configuring the file, we should restart HAProxy so that the latest changes are applied. We do this via sudo systemctl restart HAProxy. In order to test the load balancing, we'll need a client application. For this, we'll install the PostgreSQL client PSQL. However, PostgreSQL is not provided in the default repositories of Debian Linux. Therefore, we are first required to add the repository that provides the PostgreSQL package. For this, I'll simply copy-paste the commands to add the repositories. You can find them in the description. Also, we need to import the PGP key for the added repository. We also need to add the wget tool, so sudo apt-get install wget. Next, we update the package index in order to have the newest packages that came to the repositories, such as PostgreSQL version 14. Sudo apt-get update. Finally, we install the PostgreSQL client, sudo apt-get install PostgreSQL-client -14. We can confirm that it was installed by checking the version, psql version. Now, to demonstrate the load balancing, we prepared a little test. We'll make a call to the HAProxy. The IP can be found on the Google Engine page. So we copy this IP, paste it here. The port is 5432. The user is the user that we created in the beginning. The database is Postgres, and we'll use a select to obtain the IP address of the server that actually responds. For this, we'll use the following function. In this case, we get the Postgres replica that ends with 7. If we make another call, then we'll get the same IP. Here, the load is too small and therefore we don't get the other server. To overcome this issue, we'll make a call which will hold the connection occupied for 60 seconds using the pg_sleep function. Then, we open a new SSH window, and while the first server is occupied with a sticky connection, the load balancer should acknowledge that and send us to the second replica. So we make another request to the load balancer, and this time we get another server IP that ends with 5.